In this table, we see a list of the molar heat capacity coefficients, and you can see for the monatomic gases, the inert gases like helium, argon, neon, and krypton. This is a 3/2 R. R is the gas constant. For diatomic gases like H2, N2, O2, it is 5/2 Rs. This comes to 20.4. R is something. SI units. This is about the value of R here. One thing to mention here is that the molar heat capacity usually is measured experimentally. Okay, so although we can derive its value theoretically here and list that, but usually we trust the experimentally determined values more. Just like we use the specific heat capacity in chapter 11 to estimate the heat transfer, here we need CV when we study the heat input to the gas system, which played a role in changing its internal energy. Now to another important topic in thermodynamics, which is the processes in gases. We have 4 main processes. The first group of processes is called isobaric. Isobaric means the pressure is constant during these processes. So the volume may change, the temperature may change, but the pressure is kept constant. The other group of processes is the adiabatic. Adiabatic means Q is 0. It means that the system is isolated well from its surrounding. No heat can leak from the system to the outside or come from the outside to the system. So there's no thermal energy transfer from or to the system in adiabatic processes. Therefore, when Q is 0, if you examine the first law of thermodynamics, delta U is equal to W, the work, because delta U equals Q plus W. If Q is 0, then delta U equals W, the work. The third group of processes is the isovolumetric. This group of processes means that the volume is kept constant. As we know, when the volume is kept constant, this means the gas is not being compressed, is not expanding, the volume is not changing, so there is no work being done by the gas or on the gas when the volume is constant. W equals 0, therefore the change in internal energy is equal to Q for these processes. The last group of processes are the isothermal. Here the temperature is constant. We know that temperature determines the internal energy for the system. So if the temperature is constant, it's not changing, then the internal energy will not be changing. Delta U equals 0. If delta U is 0, then W equals minus Q, or Q equals minus W. Whatever change in the heat energy, it will appear in the form of work being done by the gas or on the gas, depending whether the heat energy is absorbed or released. This is an example of an isobaric process. So here you see the pressure is constant. The pressure is kept constant. This process goes from state I to state F. So the volume is reduced from this value, Vi, to this value, Vf. This is a compression of the gas. This compression process occurs at constant pressure. Because of that, we call it isobaric process. The area here, the area is equal to P multiplied by delta V. This is equal to the work done by the environment on the gas. Okay? So if the gas expands, it does work on its environment, but in that case, the final volume would be greater than the initial volume. It's opposite to this process. As for this process, this is a gas compression, not expansion. So the work done by the environment is opposite in sign to the work done by the gas. Because the work done by the environment, the direction of the motion of the piston will be during the compression going inward, while the gas applies a force in the opposite direction, upward. When we reverse the direction of motion, naturally the sign for the work will reverse. Remember that work equals force by displacement. If the force and displacement are along the same direction, work is positive. If they are in opposite directions, the work is negative. So here now we understand the isobaric process, we understand how to evaluate, in this case, the work. It is simply the area here, this area. This is the work, the change in the volume multiplied by the constant pressure. For isobaric processes, we see here a summary. So we have the change in the internal energy equals NCV delta T. PV equals nRT. This is the ideal gas law. The change in the heat energy is delta U minus W, and we know how to calculate W. So in this case, W is negative, therefore minus W is plus P delta V. So here, when we add the internal energy to the work, we are adding 3/2 nR delta T to nR delta T. This becomes 5/2 nR delta T. We may write Q as NCP delta T. Cp is the molar heat capacity at constant pressure, which is related to the molar heat capacity at constant volume by this equation. Cp equals Cv plus R. R is the gas constant. Or Cp minus Cv equals R. Cp minus Cv equals R. That is what we saw here in the table. Cp minus Cv, these values are experimental values for R for these various gases. We move on to the adiabatic processes. Here Q is 0. When Q is 0 from the first law of thermodynamics, delta U is equal to the work W. This is an adiabatic process. For these kind of processes, the product of PV raised to the power gamma is constant all the time. So if the gas changed from state with the pressure P1 and volume V1 to a state with the pressure P2 and volume V2, Then you have P1 V1 to the power gamma equals P2 V2 to the power gamma. Gamma is the ratio between the molar heat capacity at constant pressure and the molar heat capacity at constant volume. In this column of the table that we saw earlier, you see the values for gamma listed. So for monoatomic gases, it is 1.67 because CV is 3/2 R. For diatomic gases, it is less, 1.41 because CV now is 5/2 R. For polyatomic gases, it also can go lower. There it can be 7/2 R rather than 5/2 R. We move on to isovolumetric process, where the volume is kept constant. In this case, when the volume is constant, then delta U equals Q. The change in the internal energy is equal to the heat energy Q. And Q can be determined from NCV delta T. So here we are using the molar heat capacity at constant volume because these processes are concerned with constant volume. The third one is the isothermal process. Isothermal means delta T is 0. Temperature will not change during the process. If delta T is 0, then delta U is 0. If delta U is 0 from the first law of thermodynamics, then W equals minus Q. So this is the equation that we use for isothermal processes. In this graph, this is called the PV diagram. P usually on the y-axis and V on the x-axis. We see these two curves. The red curve is for isothermal process, and the blue curve is for adiabatic process. For the isothermal process, we have PV equals nRT, and for the adiabatic process, we have PV to the power gamma equals constant. The work done by the environment on the gas for the isothermal processes can be calculated from this formula, nRT logarithm V final divided by V initial. And here we have just one value for T. We don't speak of T final or T initial because T final is equal to T initial. In isothermal processes, T is constant. This is a summary. It helps us to see how delta U, Q, and W are related for these various processes. For isobaric, this is how we calculate delta U. And the Q, we calculate it using the molar heat capacity constant pressure, because the pressure now is constant for isobaric. And the work is minus P delta V. For adiabatic, again, delta U calculated the same way, NCV delta T, but the Q is 0. For adiabatic, no heat is being absorbed or released. Therefore, W is equal to delta U, because Q is 0. The third process, isovolumetric, NCV delta T, and in this case, the work is 0, because delta V is 0, so the work is 0. Therefore, Q is equal to delta U. Finally, for isothermal processes, isothermal delta T is 0, therefore delta U is 0. So Q now is equal to minus W, and W is calculated from the isothermal equation. So it is nRT logarithm V final divided by V initial. The general form, away from these four processes, delta U is determined using NCV delta T, Q is determined using delta U minus W, and W is determined from P multiplied PV area, which is P multiplied by delta V in general. In this problem, what are the different paths in the figure? So here, this path A, this represents a process that occurs at constant volume. So this is isovolumetric process. For D, this is at constant pressure. So this is isobaric process. For C, this is at constant temperature. So this is isothermal process. And B is an adiabatic process. So here the temperature changes from T3 to T4 for adiabatic processes, but the Q will not change. So this would be the right answer for this problem.